Hello and welcome to the 3D X-ray histology facility. I'm Dr. Orestis Katsamenis and I'm beamline scientist at the MUVIS X-ray Imaging Center. This is a quick tour of our imaging facility at the University Hospital Southampton, a facility which is jointly run by MUVIS and the Biomedical Imaging Unit. Here we use a non-destructive imaging technique called 3D X-ray histology, and we use this technique to image tissue specimen in 3 dimensions. The technique is based on micro-CT, which is a high-resolution variant of the well-known clinical CT. The technique uses the same principles followed by a clinical CT scanner. We use X-rays that penetrate the specimen, and we collect X-ray photographs called radiographs. These radiographs show us how much of this X-ray light has penetrated through the specimen and how much of it has been stopped by it. In order to be able to generate the 3D image of the object, we need to repeat this process again and again from different angles. In a clinical scanner, this is done by rotating the X-ray source and the detector around the patient, while in the X-ray histology or the micro-CT, what we do instead is that we keep the X-ray source and the detector fixed in space, and we rotate the specimen. Effectively, this generates the same set of radiographs, the same set of images, which we can then use to reconstruct, as we say, the internal structure of this object. In real life, the inside of a micro-CT scanner looks something like this. In one side of the enclosure, you will find the X-ray source, that's where the X-rays are being generated, and on the opposite side of the enclosure, we have the X-ray detector. That's our X-ray camera where the radiographs are being captured. Between the two components, we have our rotating states. That's where the specimen is being positioned and is rotated during the acquisition. In this particular case, a soft tissue specimen has already been placed onto the states. That's mounted on a standard histology cassette and is ready for the acquisition to commence. During the acquisition, the specimen is rotated by 360 degrees and radiographs are collected on every single step. Each radiograph contributes a unique perspective of the specimen, and when combined using computer algorithms, the inner structure of the specimen is revealed. 3D X-ray histology, here shown on the left of the screen, allows for high-resolution imaging of conventionally prepared histological specimen. As can be seen at the tissue microstructure level, the technique offers image quality comparable to this of the conventional histology, which in this example is shown on the right-hand side of the screen. Importantly though, due to the nature of the technique, 3D X-ray histology provides a unique perspective into the 3D structure of the tissues we are analyzing. As such, it has become an important research tool, and it can also play a significant role in the clinical practice in the near future. The technique is not disruptive to the current clinical workflow and not destructive to the specimen. It bridges the gap between the low-resolution 3D clinical imaging modalities like the clinical CT or the MRI and the very high-resolution but two-dimensional histology imaging. To find out more about 3D X-ray histology, visit our website at www.xrayhistology.org.